All right, so the next step is we're going to do the math to come up with an equation for the extra distance. If we're going to come up with an equation, that means we need some letters. So this next little chunk is our derivation. I've got a picture below, but bad page break. The letters we're going to use, the slits are separated by a distance that we're going to call letter D. D is usually tiny, like fractions of a millimeter. Once we start doing problems, you'll see that. The interference pattern forms on a screen. The screen is going to be a distance L behind the double slit. The L is usually large, like a few meters. When we look at a position on the screen, whether it's bright or dark, we're going to measure that distance and how far it is from that reference line I showed you. That distance we're going to call letter Y, and it's usually a few centimeters. Full disclosure, a lot of people on the internet call this one X. Maybe I should switch all my notes over to X, but I still call it Y. That's how my teacher taught me. So if you see stuff with X instead of Y, it's the same thing. They're just using a different letter. That would make more sense if I showed you a picture. So distance between the slits is letter D. The distance to the screen is going to be letter L. And when we're curious about a position on the screen, like whether this spot way up here is a bright spot or a dark spot, I'm going to say that that distance is the distance Y from our reference line. We also quantify the position of this point way over here in terms of the angle. And the angle is that line that runs straight from sort of in between the two slits and goes on an angle and hits that point. So we can also talk about the angle down here. We're going to call it angle X. So the angle between this sort of our dotted reference line and the line that actually shoots off from the middle and hits our point. It's kind of messy, but if you focus, I'll draw them and then I'll erase them so it doesn't make it too messy. If you focus on this triangle with black lines, oops, that side is L, this side is Y, and then this side doesn't get a letter. We don't really care about it, but that's a right angle triangle. We know one side is L, that's the adjacent side. We know this side over here, the opposite side is Y. So what we'll need later is from that triangle I drew in black, the tan of the angle, opposite over adjacent, so katoa, the tan of the angle is Y over L. We'll need that later. I'm going to get rid of these black lines so they don't confuse us. Now really what the question, what our proof is all about is this extra little bit down here. If we consider a point that's above the reference line, then the light that traveled through the bottom slit travels a little bit farther. Like whatever this length of this red line is, what's left over here is the exact same length, just we have this extra little bit on the end, on the end of the bottom line. That's the extra distance, and that's what drives this interference. If that extra distance is a multiple of lambda, then the two lights are in phase and it's bright. But if that extra distance is off by half, then they're out of phase and that's a dark spot. That's the diagram, but that diagram's messed up. Remember there was this artificial scenario to get the interference of light because, well, from what we talked about with sound, the D needs to be tiny, needs to be comparable to the wavelength of the light, and the wavelength of light is like fractions of a micrometer, and Y is going to be in centimeters. So D is crazy, crazy tiny compared to our Y. And the distance on our screen that we called Y is in centimeters. The distance L from the slits to the screen is measured in meters. So L is like hundreds of times bigger than Y. So basically this diagram up here, it's not wrong, just the scale is way, way, way out of whack. If I could draw it to scale and do a better job of drawing it, it would look more like this. The lines from the bottom slit, so this guy, it should be on a slightly different angle than the line from the top slit, but the scale is so out of whack that we can assume that these lines are parallel. Basically, we can assume that they're so close together that when they get to our screen would be way, 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 way over here, that this bottom line and the top line still hit at a point. Even though they're parallel, the scale is so out of whack. They look parallel, they're just coming together so slightly that we can pretend that they're parallel lines. So here's a different analogy. I'm working on my deck this week, it's going on for weeks. If I were gonna like build a deck, when I stand at my back door and look at the ground, the ground looks perfectly flat. So I can approximate the ground to be flat. But if I zoomed way out, I know that the ground is round. I know that the earth is round. But if I zoom in, then I can approximate it to be, flat. Similarly here, I know that technically the bottom line is on a slightly different angle than the top line so that they come together to a point. Just this point is so far away. It's way over to the right that even though they are coming together to a point, we can approximate them to be parallel. So moving forward in our proof, we're going to approximate that these two red lines, even though they kind of are coming together to a point, we're going to approximate them as parallel. If we approximate them to parallel, so out of this whole diagram, so we took this diagram and we're just going to zoom in on this part. That kind of is this diagram, and when we zoom in that much, we're going to assume that those lines are parallel. If we zoom in again on this part, so now we're really zoomed in. If we zoom in on that part, it looks like that. The top red line is the light from the top slit going and hitting at the point. This is the light from the bottom slit going and hitting at the same point. This is the extra distance that we're curious about. That's what I really want to solve for. If we do a little bit of math, we've got a 90 down here. Convince yourself that this angle x, whatever angle this is, the angle to our point, the exact same angle x shows up in the top of that triangle. We're kind of pivoting, so as we, let me see if I can do it. This angle is x, 90 over here. This guy, well, I don't want to mess up my diagram too much, and I'm terrible at geometry when I don't practice it. So trust me for now, and I'll do some doodling to convince you, but this angle at the top of our triangle is x. That's important because our extra distance down here, I'm choosing to call it letter D. We now know in this little right angle triangle, we know one of the sides is little d, the distance between the slits. We know the opposite side is capital D, and the angle in our right angle triangle is x. So SOHCAHTOA, we know the hypotenuse is d, little d, and we know the opposite is capital D, so sine x, SOHCAHTOA, is d over d, or that extra distance I was curious about is d sine x. All right, so we're doing great. We came up with an equation for the extra distance. The extra distance is d sine x. That's good. If d sine x is equal to n lambda, then it's a bright spot. If d sine x is equal to n plus a half lambda, then it's a dark spot. One little bit farther though, this is good because it deals with the angle x, but it hasn't brought in the L and the Y. So one more little piece to our proof. Earlier we said that the tan of x was equal to y over L. And in our last little diagram, we got that d sine x was our extra distance. It would be nice if I could do something with these two things so that I had another equation that deals with the y and the L. Right now I've just got an equation that deals with x. So here we go. This is called a small angle approximation. We used, in the pendulum proof, we used a small angle approximation. This one's a little bit of a different one. If angle x is small, so picture in your brain what the sine curve looks like from drawing it in math class. Then picture in your brain what the tan curve looks like from drawing it in math class. If we zoom in and only look at small angles like 0 to 5 degrees, 0 to 10 degrees, they kind of look the same. If we look at the sine graph, it kind of looks like this. If we look at the tan graph, it kind of looks like that. But if we were to zoom in and look at just around the origin, the sine curve looks like that, and then like does its swoopy thing, and the tan curve kind of looks like that as well. And then the tan curve shoots up and down to those asymptotes. But if we zoom in on the origin, the sine curve and the tan curve look exactly the same. So in our small angle approximation, we can say that the sine of x is the same as the tan of x. And we know that the tan of x is y over L. So our extra distance equation, we got that the extra distance was d sine x. But now we know that sine x is the same as y over L. So we can say the extra distance is also d y over L from the tan x thing. So we've got two equations, one that deals with angles and one that deals with like positions, the y and the L. if the d sine x or the dyl is a multiple of lambda, it's bright, or if it's off by half a lambda, it's dark. I'm going to put these equations down, but there's two of them. For bright spots or constructive interference, it has to be a multiple of lambda, and we've got two options. It's d sine x if we know the angle, or dy over L if we know the distances. For dark spots or destructive interference, the extra distance is off by a half, and we have those two equations for the extra distance, the d sine x or the dy over L. Don't be alarmed if this is if you're not feeling completely comfortable yet. It'll click as we start to do questions. Basically, when you look at these examples 2 and 3 and 4 down there, as I talk you through doing the examples, that'll make it really click in. Basically, the n and the y and the n and the angle, they're kind of related. Sometimes it's called the order. It basically tells you which bright spot we're looking at. If the question says a first bright spot, that means it's the bright spot that's beside the reference line. So we would say n equals 1. Or maybe a question, we'll do some as an example. A question will say something like the distance from the first to the fifth bright spot. It's referring to n equals 1 and referring to n equals 5. But since things are so evenly spaced, since our equation didn't have any squares or square roots in it, everything's nice and linear and evenly spaced. If a question asks from first to fifth, from 1 to 5, that's really the same as 0 to 4, or reference line to 4. So if a question says from first to fifth, in your solution, you can just use n equals 4. One last thing, and then I'll turn you loose to try examples, because I think seeing the examples will really help. The spacing is very, very uniform. The spacing between the dark spots is exactly the same as the spacing between the bright spots. Sometimes they use computers or light sensors to find the locations of things, and sometimes it's easier for the computer to find the dark spots instead of the bright spots. So if a question said consecutive dark spots are so many centimeters apart, if the consecutive dark spots are like 2 centimeters apart, that means that consecutive bright spots are also 2 centimeters apart. So if dark spots are 2 centimeters apart, that means bright spots are 2 centimeters apart. And if bright spots are 2 centimeters apart, that means that the first bright spot, which is n equals 1, is 2 centimeters from the reference line. So you could use n equals 1 and the constructive equation, even if a question talks about consecutive dark spots. I'm afraid that my talking might be making this worse instead of better, so I'm going to pause here. If we could get out the equipment, and I'll send you videos and pictures of it, but this is what a double slit pattern of red light would look like. So a red laser shone through a really narrow double slit would kind of give a pattern like that. Smudges of light, they're all evenly spaced. They do this cool fade off and come back. I'll talk about that once we learn single slits, but that's classic double slit interference pattern in that graphic. Take a look at these examples. I think that'll help click. There's a worksheet there. The worksheet covers a bunch of stuff. So on the worksheet, you can just look at questions 1 to 4 for now, and then a check and related double slits for you to do. I know it's a little bit weird, so take a look at the examples, and if it's still bugging you, shoot me an email and we'll figure it out together.